Okay, so people can hear me now, I'm hoping. Let me go back up. Add. There we go. Okay, can people hear me now? I'm sorry about that. I had to jump out for a second.
Yes.
Okay, so I wanted to record this. So this is actually really key. So in any atom that's not hydrogen, this little statement on the left, in multi-electron atoms, meaning anything that's not hydrogen, right? Helium has 2 electrons, lithium has 3, and so on. In multi-electron atoms, the sublevel within a principal energy level have different energies. So, and this is my statement of before we did on paper. Sublevels within a principal energy level split so that S is lower than P, is lower than D, is lower than F. So this is showing, this is in any other atom that's not hydrogen, this is actually the Auf Bau principle. I put electrons down here in the 1s, then in the 2s, then in the 2p, then in the 3s, then in the 3p. You can see the 3d is higher than the 3p, but also there's that first one that's out of sequence. The 4s is actually lower in energy than the 3d, right? Okay, let's continue. How are electrons arranged in an atom? We'll consider the ground state, the most stable arrangement. So there's this order of filling that I'm going to put electrons in the orbitals. Let me jump. Well, this is actually this is showing carbon. Carbon has 6 electrons. So I put the first 2 in the 1s. Can you guys see the arrows spin up and spin down?
Yeah. Yeah.
And then I would put the next 2 electrons in the 2s until it's full. And then in the 2p, this is actually another rule. This is Hund's rule. As we fill the electrons, when the 2p orbitals have the same energy. So why would I put the 2 electrons in this first one here when I can put them in over here? And so Hund's rule says when filling electrons of the same energy, I'll write this down later when we get back to paper, but when filling electrons of the same energy, putting electrons in orbitals of the same energy, we put electrons in singly first. So I'm going to fill the 2p sublevel 1 electron per orbital at a time until I need more space, right? Okay, so that's another rule. Okay, so, and these are some of the rules we've already covered. So electrons occupy the lowest energy orbitals first. That's the Auf Bau principle. And I can have no more than 2 electrons occupy each orbital. That's the Pauli exclusion principle. So we've already written those down. Also part of the Pauli exclusion principle is this statement over here. 2 electrons in the same orbital must have opposite spins represented by the up and down arrows. Okay. Okay, so this is showing helium. Helium is just 1s2, right? I'm going to put the 2 electrons down there. When I go to lithium, I'm still going to have the first 2 electrons in the 1s, and then I'm going to have 1 electron in the 2s. And when we get to, we jumped actually past beryllium to boron. Boron has 5 electrons. So I'm going to put the first 2 in the 1s, then the second 2 in the 2s, and then the 5th electron in the 2p. Okay. So this is the third rule. This is Hund's rule. It takes a little bit of energy to pair up electrons because there's electron-electron repulsion. So single electrons occupy different orbitals of the same energy. Well, we'll come back and I'll put that up when we'll start building these. Let's just go through the PowerPoint. 2 principles and 1 rule determine how the electrons are filled in the principal energy levels and sublevels, right? There's the Auf Bau principle we talked about. You put electrons in the lowest energy orbitals until they're full, and then you put electrons in successively higher orbitals. There's the Pauli exclusion principle that says you can have a maximum of 2 electrons in an orbital spin up and spin down. And then Hund's rule. Hund's rule says that electrons are distributed into orbitals of identical energy. Well, I don't like that statement. Let me annotate that. Hold on. That would be this one. So when filling orbitals of the same energy, electrons are put in, quote, singly first, then, quote, doubly. So before I pair them up, I'm going to put them in adjacent orbitals if they have the same energy. That's essentially Hund's rule. Okay, so with that, I've got mouse, okay. Let me erase my statement of the Hund's rule. Electrons are always filled in their ground state or lowest energy state. So, okay, very good. So this is showing carbon, which has 1 more electron than boron. So now we follow Hund's rule, right? Because boron had 2 electrons in the 1s, 2 in the 2s, and then 1 in the 2p. Carbon gets 1 more, and I'm going to fill it singly. I'm going to put it over there instead of over there, okay? And this is what we call the orbital box filling diagram. So let me, actually, maybe we could go to, here, I could probably go to paper at this point. So why don't we do that? Can I go to, can you guys see the video if I click on it?
You just have to click on it.
Do you guys have to click on the video?
Yeah.
No?
Yeah, we can switch screens by clicking on it.
Can you see the video right now?
Yeah.
Everyone see the video? Okay, well, now I need to see the video. Where's my video? There, okay. Okay. So let me bring the camera over. So there's this pattern of filling. So again, in terms of energy, we have the 1s and the 2s and the 2p and the 3s and the 3p. And before we fill the 3D, which would be up here, let's see, I guess, can we get all that on? Okay. There's the 3D. Before I fill the 3D, 1, 2, 3, 4, 5, 3D, there's the 4s, which is lower in energy. How much, are we okay on time? 4s, I think we're okay on time. All right.
Yeah.
So this is what I refer to as the orbital filling diagram. And from that, we can come up with what I call the electron configuration. And so the electron configuration, 2p5. So the big number in the front is the energy level, right? The lowercase letter is the sublevel, which includes all the orbitals that it has. And then superscript is the number of electrons in that sublevel. right? And so this is a very succinct way to talk about the anatomy of an atom, if you will. So let's just go quickly through, we went through that in the PowerPoint. So let's do hydrogen. We would put 1 electron in the 1s, right? That's the lowest we could go. And so this is the orbital filling diagram for it. The electron configuration would simply be 1s1, yeah?
Yes.
When we get to helium, second electron's gonna go where?
In the s orbital.
Yeah, spin down. So helium would just be 1s2.
1s2.
And so you notice every noble gas is basically going to knock out an energy level, right? Then we go to lithium. So the first 2 electrons are still there. The third electron, and the convention is you always put the first one in, spin up. So lithium would be 1s2, 2s1, yeah? And then beryllium, that fourth element, spin down. 1s2, 2s2. And then, let's see, so then we get to boron, and then we put the next electron in the 2p, right? So boron would be 1s2, 2s2, 2p1. There's also kind of a shortcut here, is you'll notice that the total superscript, like here, I have S2 and S1, which equals 3. The total numbers on the top have to equal the total number of electrons, right? So boron has 5 electrons. 2 and 2 and 1 equals 5, yeah? Okay. So then we saw we get to carbon, 6th element, and now we start following Hund's rule. So again, Hund's rule says you fill singly first, right? So carbon would be 1s2,
2s2,
2s2, 2p2. So notice the electron configuration does not show Hund's rule. So you only see Hund's rule when you fill out an orbital filling diagram. Let's continue. We go to nitrogen. So nitrogen, 1 more electron, I'm still going to fill singly. 1s2, 2s2, 2p3. And that's a total of 7 electrons. Let's continue. Oxygen. Where's the next electron going to go? Aha.
Back to the first one, but upside down.
Yeah, so now I'm going to pair them. So fill singly first, then doubly, right?
Yeah.
Okay, so, but again, the electron configuration won't tell me that. 1s2, 2s2, 2p4. We get to fluorine, another electron, pair it up, right? And so fluorine would then be 1s2, 2s2, 2p5. Then we get to neon, 10 electrons. The 10th one goes spin down. And notice we finished the second energy level, right? Another noble gas. 1s2, 2s2, 2p6.
6.
Okay. Now I want to go to sodium. Where's the next electron going to go?
3s1.
Good. And I typically just out of convention put it spin up first. So sodium would be 1s2, 2s2, 2p6, 3s1. And that is what's referred to as, let's get a red pen. Where's my red? Red go. Huh. This is what we call the full electron configuration. Can you guys see the red okay?
Yes.
Yeah.
Okay. So sodium, that's the full electron configuration. There's also what they call the condensed electron configuration, which is, let me put that. So let's rewrite sodium. So the condensed electron configuration oops. For the condensed electron configuration, you put, let's say it this way. You remove all electrons of the previous noble gas and write the noble gas in brackets. Okay, so I'll come back to that. I want to come, let me come up here so we can see that if we want to see it in a second. So this is the full electron configuration of sodium. What's the noble gas before sodium?
Neon.
So another way of writing the electron configuration is sodium's electron configuration is brackets neon, which is everything neon is, which is 1s2, 2s2, 2p6, and then what else does sodium have that neon does not have?
3s1.
3s1. And so this is a shortcut. I really like that. This is the condensed electron configuration. Okay?
Mm-hmm. Mm-hmm.
All right. I think we're doing well here. I want to continue with a couple more ideas, and then I'm going to go back to the PowerPoint because it shows that you can actually use the periodic table here. So I just a couple more ideas here. So so sodium can be 1s2, 2s2, 2p6, 3s1 full electron configuration, or neon 3s1 condensed. By the way, all these configurations we're doing are what we call ground state. And because we're following all these quantum mechanical rules, the ground state, the Auf Bau principle says you put the electrons in the lowest energy orbitals first and so on. But you can have an excited state. Sorry, that's screwed up. Excited state. So in an excited state, basically you have one or more electrons above the ground state. So I'm probably not going to test on this, so I just want to mention it. I don't know if it'll show up in the homework or in the book. It could, but just to kind of mention it in passing. So sodium excited, and sometimes they'll show it with a little star. Maybe 1s2, 2s2, 2p6, 4s1. You guys see this? So basically I have one electron above where it should be, right? Does that make sense?
Mm-hmm.
And so in atoms in the real world, that's happening all the time. The atoms are absorbing light and the electrons jump up to higher energy levels and then they fall back down and so on. So we could talk about an excited state, right?
Yep.
And these are allowed as long as they're not violating quantum mechanics. Okay. Let's go back to, if you guys don't mind, I want to go back to the PowerPoint again, okay? Is that all right?
Yeah.
Okay, so I'm gonna, if you can, can you see the screen still?
Yes.
Okay, so if you guys can see the desktop, let's bring this up. So we were doing carbon. Let's go back. So this is showing all of them up to neon. This is this order of filling that we just did, right? Following those quantum mechanical rules. So you have the orbital. I have 10 minutes. So again, someone let me know when I hit the 1 minute mark, okay?
Yep.
All right. So, so there's the orbital filling diagram. There's the electron configuration. Here's silicon. This is further ahead. Oops. Let me click ahead here. Okay. So let's just see this. So there's a pattern here. So if I look at this, lithium's 1s2, 2s1, sodium's 3s1, potassium's 4s1. Do you guys see the pattern I'm seeing?
Yes.
Yeah.
Yeah. All of the alkali metals are S1 with their highest energy level. Do you see that?
Mm-hmm.
Yeah.
Okay, good. What about alkaline earth metals, what we call the 2A? They're all
S2s.
S2. Beryllium's 2s2, magnesium's 3s2. That shouldn't be that's a typo. That's
be
a screw up on the PowerPoint, and I'm sorry.
Calcium.
That should be calcium, right?
Mm.
That makes sense?
Yeah.
They screwed up. 2A is calcium. Oop. Okay. Anyway, well, whatever. Let's just leave it. But all the 2A's are S2. Oops. Right. Okay. All of the halogens, all of the 7A's are S2P5. See this? Fluorine is 2S2, 2P5. Chlorine is 3S2, 3P5. Bromine is, if I exclude this intervening 3D, it's 4S2, 4P5. Yeah?
Mm-hmm.
Okay.
Yes.
All right, good. All the noble gases, with the exception of helium, are S2P6. So helium is 2S2, 2P6. Argon is 3S2, 3P6. Krypton, if I ignore again that 3D, is 4S2, 4P6. So there's this pattern we see. And so this is the second mnemonic, is the periodic table is your mnemonic. So if I look at the 1A are always S1, the 2A are always S2. And so the 1A and the 2A are referred to as the S block. And the 3A through the 6A, I'm sorry, the 3A through the 8A, if I exclude helium, are the P block, right? Helium's kind of an exception. It's 1s2. So electrically, helium should be in the 2A. It's put over, why is it put over in the 8A? Why is helium in the 8A? Its electron configuration doesn't match.
There's a gas?
Because it's a very unreactive noble gas. And helium does have a full energy level. It just, there is no p orbital in the first energy level. So at any rate, the p orbitals are they're filling their p's. So so everything in the 3A would be P1, everything in the 4A would be P2, 5A, P3, 6A, P4, 7A is always P5, right? All of those halogens. And everything in the 8A would be P6, right? Down here, so, and it's also, it's no mistake that these first two columns are too wide. There's only, how many electrons can I have in an s orbital?
2.
2, right? In how many p orbitals are there in a sublevel? There's 3 p orbitals, right? So how many electrons can I have?
6.
6. So it's no mistake that this block is 6 wide. How many orbitals are in the d block?
7.
7.
That's the f block. D is 5. So how many
5.
electrons can I have?
10.
10. So it's no mistake that this D block down here is 10 wide, right?
Yeah.
Okay. And then the F block, there's 7. So the F block is actually 14 wide. I can have 2 electrons in each of the 7 orbitals. There's kind of some tricks for this. Let me put text here. So for the S and the P that I'm filling, let's do it this way. The energy level, let me widen this out. The energy level is equal to the period. So if I'm in the first period, I'm filling the 1s. If I'm in the second period, I'm in the 2s. What if I'm in the 5th period?
Fifth period.
5th period would be the 5s.
Yes.
What if I'm over here in, let's say, this spot right here? That would be 3p4,
P4.
right?
Yeah.
Because it's 4 electrons into the p block of the 3rd energy level. What about, can you guys see my cursor? What about this one? What would that be?
2p2.
2p2. Okay, let's go down. What about this one here?
2p.
Wait, it's not 2. It's in
No,
the
it's
6th energy
6.
level.
Yeah, it's 6p5.
What?
5. Yeah? Okay, let's
Yeah.
count in. What about in the D block? Okay, so for the D, the energy level is equal to the period minus 1. So if you guys, so we go 3s1, 3s2, 3p1, 2, 3, 4, 5, 6. That's argon. And then I fill the 4s1. That's potassium. Potassium's 4s1. Then calcium is 4s2. And then this would be what right here?
40.
That would be 3D because it's the period minus
Okay,
one.
Minus 1. Yeah, so yeah, 3D.
Yeah, this would be 3D1, right?
Mm-hmm.
3D2. And so on, right? And I get all the way
Yeah.
over to here. This would be what?
3D9.
Well, that would actually be
No.
D10.
10.
Yeah.
Well, it would be 9.
Let's continue. Okay. So what about this one right here? What would that one be?
5D4.
Perfect. Yeah?
Yeah.
Okay. So the D is the energy level minus 1. Let me go back up to here for a second. The F is
minus 2.
Minus 2, exactly. Who said that? That's excellent.
We have less than a minute.
I can't hear someone saying something. If you want
We
to,
have
Less
a
than a
minute
minute.
left.
okay. So what I'm going to do is copy this so I can repaste it. Thank you for telling me. Okay.
And the class is almost over.
Okay. Well, we basically covered electron configuration. Do you guys want to jump back in?
Yeah, fine.
Well, let's jump back in. I'm going to end it and jump back in. How much time have we got? Oh, we still have like 4 minutes. So let's jump back in. Okay.
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 All right.
Me too.